Okay, so this talk is going to be about simple constructions of linear depth t-designs and pseudorandom unitaries. And this is joint work with Tony Metger, Makrand Sinha, and Yuen. Okay, before we start, let us first briefly recap what a quantum computation is. So quantum computation is nothing but a unitary operator that acts on a finite dimensional complex vector space. Okay, and a unitary operator is always reversible, meaning there exists an inverse unitary that essentially undoes the unitary operation. And you can also think of it as a change of basis. It takes a complex valued vector and maps it to a different complex valued vector. Okay, and one thing that's important to note about the unitary group is that it is, in fact, a group under matrix multiplication. So the set of unitaries acting on n qubits form a group, and this is what we call the unitary group. Okay, so a natural idea is to think of a random unitary. Okay, so in order to make sense of what a random unitary is, well, we first have to revisit this idea of the Haar measure. So it turns out that the set of unitaries is a continuous set, and the probability distribution over this continuous set is non-trivial, but it's still fairly well understood, and it's called the Haar measure. And the Haar measure is essentially just a unique, unitarily invariant probability measure over the unitary group. Now the question is, can we implement Haar random unitaries efficiently? Okay, and unfortunately the answer is no, because as Knill showed in 1995, most unitaries actually have exponential circuit complexity. Okay, so this means that, if you sample a random unitary with overwhelming probability, it will actually be highly complex. Okay, and this is not too surprising given that, Shannon's counting argument already showed something like this for Boolean functions. Okay, but is this the end of the story? Well, it turns out we can de-randomize the Haar measure. And this brings us to this idea of a unitary t-design. So what is a unitary t-design? Well, you can think of it as the quantum analog of a t-wise independent function. Okay, so it essentially matches real randomness up to t moments. Okay, and the way we define this is to say that, a ensemble of unitaries forms a unitary t-design approximately if, in terms of the diamond distance, the twirl over the ensemble nu is roughly the same as the twirl over the unitary group, provided that I only look at t copies of the unitary at the same time. Okay, and unitary t-designs actually have very nice and efficient constructions that consist of circuits that are polynomial in n and t. Okay, so in seminal work by Brandau, Harrow, and Horodetsky, they show that random circuits of a sufficient depth, which scales polynomial in n and t, forms a t-design. Okay, and later this was improved by Jonas Haferkamp, who showed that actually, only a depth of t to the power 5 is sufficient. Okay, and there have recently been some nice developments that, managed to reduce such depth even further. So there's this work of Ha, Liu, and Tan, who showed that random Pauli rotations in depth that is quadratic in t forms a unitary t-design. And then there was also the work of Chan, Doctor, Zhu, Bulin, and Hayden, who showed a similar scaling using a completely different approach based on exponentiated Gaussian unitary ensembles. But the big open question is, can we actually get t-designs with depth linear in t? Turns out that this is essentially optimal, and it has been a long-standing open problem to construct unitary t-designs that have, the optimal t-dependence in depth. Okay, so to summarize part 1 of my talk, Haar random states and unitaries have exponential quantum circuit complexity on average. And this requires de-randomization in order to, sample such random unitaries efficiently. And the most natural notion of de-randomization is this notion of a unitary and state T design. Okay, and there we can actually achieve efficient ensembles that have polynomial dependence on n and t, provided we know n and t. Okay, but this suggests that we have to know n and t in advance, and this will not be efficient for very high order t. So then the question is, can we de-randomize even further and essentially match all moments of the Haar measure? And this brings us to the second part of my talk, quantum pseudorandomness. And here we study this notion of pseudorandom unitaries. Okay, so this is a concept that was first introduced by Yuen. And the idea of a PRU is that it's essentially just an ensemble of unitaries that forms a super high order T design under computational assumptions. Okay, so it's an ensemble of unitaries U sub k that are indexed by a key with the following two properties. So first of all, there's an efficient algorithm that, given the key and an input state, can apply the unitary according to k onto this input state. And the second property is pseudorandomness. So this unitary U sub k for random key k is actually indistinguishable from a Haar random unitary. Okay? And here we require this to hold for any computationally bounded observer. Okay, so you can think of a quantum algorithm here. So what this means is that in practice, if you have a quantum algorithm that performs some quantum computation, it may make a bunch of measurements, and this quantum algorithm can essentially query this unitary, so it can make use of the unitary during its computation. And the way we model access to the unitary is to say that there essentially is an oracle, and the algorithm can consult the oracle, give it an input, and the oracle will reply with the unitary applied to that input. And so in this oracular model, we say that an ensemble of unitaries is secure if no efficient quantum algorithm can detect whether it is in the real world, where it is given a unitary U sub k, or whether it is in the ideal world where an actual Haar random unitary was used. Okay, and one thing that I'd like to point out is that despite the fact that Zhi and Song introduced this primitive, it has actually been open to construct a PRU since 2018. Okay, so what is the difference in the difficulty of constructing PRUs as compared to unitary T designs? Well, if you want to construct a unitary T design ensemble for a certain T, then you're pretty much required to set the parameter T in advance. Okay, if you need to determine whether you're going to use a random circuit of a certain depth, then obviously the depth of the circuit is dependent on T. So you kind of have to know T in advance. But what's nice about a PRU is that the construction is formulated in such a way that T as a parameter never comes in. Okay, so we don't require any a priori bounds on how many copies of the unitary we want to make available. So potentially for high order T, a PRU is really, out-competing a unitary design in terms of efficiency. However, as long as the number of copies or queries to U is T or less, turns out that unitary T designs actually cannot be distinguished from Haar by any measurement. Okay, it's an information theoretic statement. But for PRUs, the story is a bit more complicated because, we have to resort to cryptographic assumptions here. And so we conjecture under certain cryptographic assumptions that there is no way for an efficient algorithm to distinguish the two. But in principle, there could exist a measurement that actually does distinguish the two. But most likely such a measurement requires exponential amounts of computation time. Okay, just to summarize the second part of my talk. So pseudorandom unitaries are extremely efficient scramblers. and they essentially match all moments of the Haar measure under cryptographic assumptions. And here by all moments, I mean all moments that you might encounter in practice, so that are somewhat polynomial in the number of qubits. So this holds for all practical purposes. And unlike pseudorandom states, which are fairly easy to construct, PRUs are actually, harder in the sense that they do require complex numbers, which, really limits the choice of natural constructions that one might want to consider here. But then the question is, can we tweak prior constructions and get actual PRUs? Okay, so in our work, our first contribution is we give a non-adaptive pseudorandom unitary. Okay, so this is the first construction of a pseudorandom unitary that has provable security. And as a second contribution, we give a simple and linear depth unitary T-design, okay, thereby finally getting a construction of a unitary T-design that has the optimal T-dependence, which is linear. Okay, so here is the main contribution. We give an ensemble of unitaries that has the following security property. If I apply T copies of the unitary on an input state, which is potentially entangled with a reference system, then this behaves as if I had applied a Haar random unitary to the same state. Okay, the two are computationally indistinguishable. Okay, so what this essentially means is that we provide a non-adaptively secure PRU. As long as we consider parallel queries of this form, our construction will be secure. Okay, so here again, we assume that no computationally bounded adversary can distinguish between the two. Okay, and how do we achieve this? Well, here's our main construction, and it's surprisingly simple, and we call it the PFC ensemble. So our ensemble of unitaries consists of three operators. The first is a pseudorandom permutation operator, okay? It essentially just takes a quantum secure pseudorandom permutation and applies it in place. Okay, it's a reversible operation, one can apply it in place. The second operator is a pseudorandom phase operator. Okay, so this is a phase operator that applies a pseudorandom function with single bit output in the phase. And the last operator is just a random Clifford operator, which can be sampled efficiently. And we claim that these simple three operators give rise to a pseudorandom unitary. Okay, so this brings me to part 3 of our work. Turns out that our construction also implicitly defines a simple and linear depth unitary T-design. Okay, so how do we show this? Well, here the idea is we just get rid of the computational assumptions and instantiate the permutation and the phase function with their two T-wise and T-wise independent counterparts. Okay, so instead of a pseudorandom function, we now take a two T-wise independent function. And instead of a T-wise independent permutation, instead of a pseudorandom permutation, we take a T-wise independent permutation. Turns out that those only exist approximately, but this suffices for our setting. And the crucial thing is that these two only require depth, which is linear in T, which is exactly what we wanted. And then the unitary T-design is just the same operator from before, just instantiated using different building blocks. Okay, let me briefly describe the proof idea behind the PFC ensemble. Suppose we have an n-qubit state psi, and we have T many registers. Okay, so in total we have, T times D many qubits. T times N many qubits. And the claim that we make, the initial claim, is that a so-called T-fold Clifford twirl has the following property, namely, if we apply it on this input state on T many n-qubit registers, then the T-fold Clifford twirl will guarantee that the resulting output state has almost no weight on the subspace that corresponds to collisions. Okay, in other words, a random Clifford surgically removes all of the collisions in the state with overwhelming probability. Okay, provided that t is much smaller than d. Okay, this is a very simple calculation. And the intuition here is that collisions are kind of a two-body problem. But the Clifford is a 3 design, so in particular, it's a 2 design, and therefore it sort of behaves just like a Haar-random unitary, and this gives the desired property. Okay, but then if we can assume that the resulting state has no collisions, we are essentially in the distinct subspace. And there, the analysis is much easier. And there, all we have to show is that the average state that we get when we twirl with permutation and phase operators behaves just like the average twirl over Haar-random unitaries. And this statement turns out to have a nice solution that uses representation theory. Okay, so here we use this idea of Schur-Weil duality to decompose these states into irreps that we can then much more easily compare. Okay, so just to recap, the goal is to show that the two twirling operations behave similarly on any input state. Okay, and what we're going to do now is to use Schur-Weil duality, which tells us how to partition the underlying vector space that these twirls act on into subspaces that are indexed by irreps. Okay, irreps of the symmetric group and the unitary group. And then using representation theory, we can write the Haar twirl under a change of basis as a sum of blocks. So the operator will become block diagonal if we perform the right change of basis. And this block diagonal operator has a very nice form. Namely, it's essentially just a sum over all of the irreps. And in the so-called Weil module that corresponds to the irreps of the unitary group, the resulting output is essentially just a maximally mixed state in this specific subspace for each lambda. Okay, and then it turns out if we do a similar expansion for the permutation phase twirl, we find that the resulting state almost has the same form as the Haar twirl. The only difference is that the maximally mixed state sort of lives in a smaller subspace. Okay, so it occupies a large part of the Weil module for every lambda, but it doesn't fill it all the way. Okay, so there's some discrepancy. And so in our proof, we just observed that the discrepancy between these two can just be bounded by a quantity which vanishes in the number of qubits, provided that t is sufficiently small. Okay, so this brings me to the summary of part 3. So we showed that the PFC ensemble instantiated with a pseudorandom permutation and a pseudorandom phase operator and the random Clifford forms a non-adaptive PRU. And we showed that the same ensemble also gives rise to a simple linear depth T design when instantiated with two T-wise independent functions and two T-wise independent permutations. Okay, and in the end, I just want to highlight that there have been a number of follow-up works that make use of our construction. Okay, and so now I want to thank you for your attention.